Today I'll talk to you a bit how we do our global load balancing at Facebook. I've done this talk in the past, and somebody came up to me right before the talk and asked, how technical is your talk going to be? And my answer was, as technical as you want it to be. So I really encourage you guys to ask questions, both after I'm done with the slides and then afterwards. With that said, 25 minutes is a very small amount of time to talk about global load balancing in super detail, but we will go into the layer 3, layer 4, layer 7 protocols a bit. And another thing I want to point out is we do use a lot of open source software in our global load balancing stack. So most of the things are open source, but the things that aren't are very easily done with open source components. So when people ask me what a traffic engineer at Facebook does, this is the mental picture that comes to mind. This is a map of the world showing all the people who use Facebook and all of their connections to all the other people in the world who use Facebook. So our job is when they get on their web browser and type in facebook.com, or they open up their phone and open the Facebook app, we're responsible for getting them, directing them to the closest server to terminate TCP and SSL, and then proxying those requests, whether dynamic or static requests, back to Facebook. So kind of what we'll be talking about today. First is we'll go into how we actually serve dynamic requests on the Facebook. We'll talk about what a dynamic request is in just a moment. We'll actually dig into the layer 3, layer 4, and layer 7 load balancing that we do, the IP and IP encapsulation, TCP routing, and all that. Next, we'll actually go and talk about our edge POP location, how we reduce latency. POP stands for point of presence. Lastly, we'll talk about our global DNS load balancing, and then we'll open it up for Q&A. So traffic at Facebook. If you all went to the networking slide that Jose and David did this morning, I blatantly ripped this off of them. It's a fantastic slide. But the important thing I want to just point out here is every day, on average, we have 936 million people that use Facebook. And every day, we have 798 million people on average who use Facebook. That's a heck of a lot of people. And approximately, again, from the earlier talk, 82.4% of those daily active users are outside of North America. So this actually, when I see these numbers, they're great, but I start thinking in traffic perspective. We actually have to get all of those people who use Facebook to our servers. So what is Facebook from a traffic perspective? We have two types of requests kind of in general. We have dynamic requests, which are like newsfeed, likes, status updates, all that. So these are requests that are actually going to hit an HHVM. We'll talk about that in a little bit. An actual web server inside of one of our data centers. And then we have static requests. So these are all the CDN, content delivery network requests we do. So photos, videos, all the content that doesn't change each time you actually request it. So with all of this combined, we actually do terabits of egress to the internet per second at any time during the day. So today, we're only going to focus, just because of the time constraints, only on dynamic requests. So I want to define what we're actually talking about. So today, as I mentioned in the previous slide, we're talking about when you open your phone, open up the Facebook app, how do we actually get to you to an HHVM web server? So HHVM is a hip-hop virtual machine. It's our JIT VM for running PHP and hack code. So what we're not talking about today is all of the load balancing once you actually have hit that web server and all the stuff behind it. We have a lot of really awesome stuff. We do a lot of load balancing and sharding, but that's all out of the scope of this project, for this talk. So again, our job is to, when somebody opens up Facebook, terminate TCP and SSL, and proxy their request back to HHVM. So this is what it looks like. Our weekly egress cycle looks like. Egress is bits per second, leaving our routers to the open internet. It kind of show every week. You can see two lines there. One is this week, and we always show it overlaid on top of the previous week. It's really crazy how well it actually maps to the previous week. So even though they have very different curves, each week they're very similar curves, which is kind of crazy, unless it's like the World Cup, and then it's all over the place. Ingress is at the bottom, so those are actually bits coming in per second. So we send out a heck of a lot more bits than we take in. So looking at one day, a 24 hours view of our egress, it's a diurnal cycle, which is a fancy way of saying a cycle that actually follows the sun. So this pattern repeats itself every 24 hours. We can see the peak about 8 p.m. In the time here, which is about noon on Pacific time in the US. So you can see the peak, and then it comes down, and then peak in the US again, or in North America, and then it goes back down again. And these time zones here are all in Pacific time. And what egress actually is, it's the sum of all time zones in the world. So if you actually break it down by Europe, APAC, North America, you can see each line has their own kind of unique pattern. So I think everybody in here is an SRE, so I'm really quickly going to go over TCP and IP. I assume you guys are all very familiar with this. We're going to talk about layer 3, layer 4, and layer 7 today. So layer 3, IP, Internet Protocol, route packets across the Internet. Layer 4, TCP, the transmission control protocol. And layer 7, for today, we're only going to talk about HTTP, but we also do support, with all of our load balancing infrastructure, both SPDY and MQTT. So quickly, IP header, a lot of information. We do some really interesting things with IP inside the POPs, but it's out of scope for this talk. So today I'm just the only two important pieces are the source address and destination address. TCP header, a lot of different fields there. The only thing that are important for this talk are source port and destination port. Layer 7, HTTP requests, very simple GET requests. So putting it all together, you have your layer 7 encapsulated in layer 4, encapsulated in layer 3, and then that's what the internet is routed upon. So for the remainder of this talk, this is a lot of information here. For the remainder of this talk, I'm just going to simplify this, and this is how we're going to talk about the packets, the actual requests. So cool. So how do we actually serve dynamic requests within a Facebook data center? So we're going to start off by just assuming we have one web server that serves all of Facebook for the entire world. So whip out your phone, open the Facebook app. It's going to hit a quad A record. So IPv6 request for Facebook.com. It's going to return a quad A. And it's also interesting to note is like we do over 10% of our egress with IPv6. And we do over 100 terabits per second within our data centers in all of our regions. So we're very heavily invested on IPv6. So then your phone will actually go and hit a web server. So it's going to hit this single web server. Everybody's going to hit it, return HTML. But one web server is not going to be able to scale for us. So we need to figure out how to scale this out. So what we do is we add a load balancer. We had a load balancer in front of it. In our case, this is our L7 load balancer called ProxyGen, and I'll refer to it as ProxyGen throughout the talk. So what ProxyGen is actually going to do, the request is going to come in, it's going to terminate TCP and SSL and reverse proxy that back to an HHVM server. Actually, a whole bunch of HHVM servers. It's not on here, but we do use Zookeeper as our service discovery mechanism here. So this is great. We get a lot more RPS, but one single L7 load balancer is not going to be able to handle all the traffic. So what do? We had another load balancer. So here's our L4 load balancer, and this is using IPVS, which is IP Virtual Server. It's an open source kernel module that does L4 TCP routing, essentially. So here, now the packet's coming in, the IP packet. I'll talk about what's actually happening here a little later in the talk, but it's IP and IP encapsulation. Packet comes in, it gets consistently hashed to the L7 load balancer. TCP and SSL is terminated, and then that request is served. So this is great, but one IPVS server is not we can't just go with one server. It's not scalable. We can't serve all the traffic with it. So what do? We actually add another load balancer in front of that. So here we're using the router's ECMP to consistently hash. So ECMP is equal cost multipathing. The IP packets come in. They get consistently hashed to the IPVS server, to one of them. And then those will get consistently hashed to the L7 load balancer, terminate TCP and SSL, and serve the request. So this is great, but this is what the makeup of a front-end web cluster looks like at Facebook. So to kind of take a look, this is kind of the scale of what it looks like, but we have tens of IPVS servers. We have many hundreds of ProxyGens and many, many thousands of the actual HHVM web servers. And it keeps going on. We got a lot of them. So one cluster is really great, but we can't serve all of the world's traffic with one cluster. So what do? We add another cluster. So we'll have multiple clusters, and this is the concept of a data center. So a data center in Facebook's terms is multiple clusters. And we do have more than one. This is just a typical front-end cluster. We do have also a bunch of other types of clusters, service clusters, database clusters, et cetera, out of scope for this talk. So this is great. Having a data center is really nice, but we need to get more RPS out of it. So we add another data center. So this is where we do our DNS load balancing. So we'll add more, based on the capacity of this data center and many other factors, we will load balance to the data center. So one important thing I want to mention is this isn't really a top-down approach. We've kind of seen it in line, but when we use like as I understand, like a Mesos Kubernetes type of job scheduling engine. We call it Tupperware. There's been a talk on that before. So these servers actually will live right beside each other, and we just use BGP to actually announce them up and have their IP addresses available. Not the web servers don't use BGP, but the the IPVS servers do. Here we go. So here's our different data center locations around the world where all of our front-end clusters live. So now let's actually dig in and kind of look at what's actually happening with the load balancing. So breaking it down, this is kind of the flow we've already seen. Again, we're only going to look at layer 3, layer 4, and layer 7 right now. And in this case, layer 7, as I mentioned, is ProxyGen. Layer 4 load balancer is IPVS. And then ECMP is kind of a layer 4 load balancer as well, consistently hashing. It does consistently hash on the TCP flow. So it does use the TCP port, source and destination port. So the way this works is we have our L4 load balancers. They're sitting there. And then the way they actually come online is they will BGP peer with the router. So they will BGP peer a /32, and I believe it's /64 for v6. And they will BGP peer to the router, and then the router will then ECMP hash to the IPVS servers. So the packet will come in. And then from there, the L4 load balancers behind that, we will use service discovery. Again, we do have some abstractions on top of Zookeeper for the L4 load balancers to discover the L7 load balancers. Another important thing I want to mention here is the L4 load balancers, like I mentioned, the way they get IP reachability is they BGP peer to the router. The L7 load balancers, they all listen on the same VIP that's actually being announced to the internet, but they listen on the the loopback device. So they're not listening on any of the Ethernet devices. They are listening on the loopback, and we'll talk about why we do that in just a moment. So let's actually look at an example of an IP packet coming in, a request coming in from one of our clients. So the request comes in for the newsfeed. So the IP packet's going to come into the L4 load balancer, and then it's going to take that packet. It's going to consistently hash it to one of the L7 load balancers based on source IP port and destination IP and port. And then it's actually going to take that and store it in its hash table, so a state table. So our IPVS servers do keep state of all the flows that are going through. So all those requests that are going to come in, they should get ECMP hashed to the same IPVS server, which will get also consistently hashed to the same layer 7 load balancer. So this is obviously very important for establishing TCP. So somebody else comes in from their browser, request comes in, it gets consistently hashed to one of the L4 load balancers, which gets consistently hashed to the L7 load balancers. So this is all great. So what happens if we actually lose one of our IPVS servers? So that request is actually going to come in to the other IPVS server. So request comes in, and since we're doing a consistent hash, and assuming the state of all of the servers, the L7 load balancers are the same, it's going to get consistently hashed to the exact same server. So we can actually keep our TCP state established. And then the state table, that device will also be in the state table for that IPVS server. So what happens if we lose connectivity to one of our L7 load balancers? So the request will come in, and since that load balancer is down in our service discovery, that client request will get sent to another L7 load balancer, consistently hashed. So this is great. Everything works. But what happens if that L7 load balancer comes back? So the request will come in again, and it will actually continue. Since we do keep state of all of our TCP flows, it will continue to go to that L7 load balancer. So one of the kind of things I glossed over here is we actually do DSR, so it's direct server return. It's just a way for us to kind of take the L4 load balancer out of the loop. So we'll walk through how this works in just a moment. But the request comes in, it goes to the L4 load balancer, and we use IP and IP encapsulation, which I'll show you in just a moment. It will go to the L7 load balancer. The request will be served by HHVM, and that IP packet will actually egress directly from the ProxyGen. So on the return path, we take IPVS completely out of the loop, the L4 load balancer. So you saw this earlier in the talk. So when that packet actually comes into IPVS, what we do is we take it, we look it up in the state table, and if it's not there, we'll hash it and put that in the state table. And then the destination L7 proxy gen that this is destined for will actually encapsulate that packet inside of another IP packet. So this is essentially what IPVS does, IP and IP encapsulation. So again, so that request comes in from the mobile client, it hits our L4 load balancer. The L4 load balancer determines the correct server to, the correct L7 proxy to send it to, wraps it in an IP packet, and then sends it off. So once that packet actually lands on the L7 load balancer, since it's destined for that unique IP address, it will actually take it, it's like, yeah, this is mine. And then it will de-encapsulate it. It realizes it's an IP and IP packet. It will take it, take off the outer IP packet, and it'll drop it back on the network stack. And then since our layer 7 load balancer is listening on the loopback device, it says, yes, I do actually have this. And then it will serve the request, and then it will egress back directly to the device. Cool. Any questions so far? I think we're doing pretty good on time. Okay, no questions, good. So now let's talk a little bit about edge pops and how we reduce latency by deploying servers closer to the people who are using Facebook. So this is what the round trip time looked around 2011. We found that all of our data centers at the time were in North America, and we found that the folks that lived in North America had a much better experience on Facebook. And this is a graph of the round trip times around that time. So what the traffic team did at that time was they kind of figured out or tried to determine like how do we actually reduce round trip time. And the answer there was to deploy edge locations in internet exchanges and colos around the world. So let's take a really, let's look at an example here. So let's have a person using Facebook in Seoul, and they want to hit, assuming we only had data centers, they want to hit our Oregon data center. So the distance between Seoul and Oregon is approximately 75 milliseconds. So just to establish TCP, you send, SYN-ACK, ACK, it takes 150 milliseconds just to establish TCP. So SYN, SYN-ACK, ACK. And then you also have to think about SSL. So that three-way trip, just to establish TCP and SSL, that's 450 milliseconds, and all those packets have to travel across the Pacific Ocean. And then by that time, you finally get to send your HTTP request, and overall, it takes 600 milliseconds just to have one simple HTTP request. So now let's look at an example. If we have a POP in Japan. We'll look at the exact same kind of diagram here. Between Seoul and Japan, it's approximately 15 milliseconds. So here, all we have the clients do is establish TCP and SSL only within the region. So here, within 90 milliseconds, we've already established TCP and SSL. And at that point, we can send our request. We reverse proxy it. So this is what hits ProxyGen. This area, that line in the middle there is Shiv and ProxyGen. That request will get proxied back to one of our data centers to be handled by HHVM, and the request will be returned. So all in all, just by putting a server within the continent, we've reduced the RTT by over half. So here is a map of all our different edge pop locations around the world, and we're continually building them out as quickly as we possibly can. So how do the load balancers and the POPs actually work? So the examples I was showing before just was mostly our load balancing inside the DC. The good news is we use the exact same software stack inside our POPs. So the IP request will come in, hit our router, be ECMP hashed to one of our L4 load balancers, IP and IP encapsulation to our L7 load balancer, so TCP and SSL is terminated. But the difference is we don't have HHVM in any of our POPs. So what happens is that request will go back to one of our data centers. So we have pre-established HTTPS connections to all of our data centers. So those requests will get proxied back to our to the exact same stack. So this is what I was talking about before. It goes into the router, ECMP, IP and IP, terminated TCP and SSL, and then HHVM will serve that request. So now let's talk a little bit about how we do DNS load balancing. So Cartographer is our kind of the workhorse behind how we map the world, our view of the world in terms of NetBlock to our edge pop connectivity. So again, here's an image of our edge pops. We want to. The goal is to get the client connected to the POP that is closest to them. One of the important caveats there is distance doesn't always mean that that POP is the closest to them. The internet is kind of clowny sometimes, and your IP packets will travel all around the world for no good reason. So what we want to do is we want to send that request to the closest edge location. There's a lot of things to consider there. One is capacity. Do we actually have enough physical resources, CPU, memory, network, to actually serve that request? Another, is that POP actually healthy? We have a global monitoring infrastructure to check these from all around the world, which will return back if that's unhealthy. So that goes into our DNS load balancing decision. And then we also, if we don't have any better information, we will use some geodata to actually serve that, or to map them to the closest location. So how do we actually measure the closeness? As I mentioned, physical distance doesn't always mean you're actually close to our POP. So we use sonar to do this. And so what sonar does is one in every approximately, I think, 80,000 requests for profile pictures, we will actually send that request to a suboptimal POP location. So you will not go to your nearest POP. So throughout the day, this actually creates a heck of a lot of information. And the way this works is we'll send you a unique URL. So we'll give you a unique URL, which is going to be guaranteed to go through your recursive DNS resolver. And then from there, that will hit our DNS resolver. So we're able to map your client IP address with the DNS resolver you're using. So it generates a heck of a lot of data, and it's a really nice mapping from client IP address to ISP resolver they're using. So the way Cartographer works, as I mentioned, it takes a lot of different inputs: capacity, the latency between our DNS resolvers that are talking to us, the actual routing. It does peer with every router we have, every border router that's going on the edge of the internet, and collects all the routes to see how things are looking there. And of course, it does periodically, actually continually, ping every single L7 load balancer that we have to collect that health data. And then so what that does, all those inputs are done. It creates this DNS map of the world. So based on your net block to our nearest edge locations. That file, that map, is then torrented out to all of our DNS servers all around the world. And I don't think I mentioned it, but we do use Anycast DNS, UDP, to serve requests. So those, and we use TinyDNS as well for our DNS server. So it will be torrented out to all of our TinyDNS servers throughout the edge infrastructure. And then from there, based on the ISP DNS resolver, or whatever DNS resolver you're using, we'll return you to the nearest, most optimal upload location. So here's kind of another way to look at it. Cartographer does its offline processing, generates the map, loads that into DNS, and then all the different ISPs that are actually, or the recursive resolvers that are hitting it, it will return return IP addresses for the nearest location. So here's Cartographer in action. This graph here, it's a little bit difficult to see, but that red line is the actual traffic that would go to this POP if Cartographer were not working. This green line here is the capacity limit that we've defined. We cannot go over this RPS limit, so RPS requests per second. So this is a view of 24 hours of Cartographer working on one of our POPs, and you can see that squiggly blue line there. That's Cartographer actually keeping it right where it needs to be throughout the entire day. And another important fact that I didn't mention is Cartographer will regenerate a map approximately every 5 minutes. So it basically takes all those inputs, snapshot in time, generates the map, torrents it out, and then does the exact same thing again. So we're able to very quickly iterate and kind of measure where our traffic is going. So here's an example of a bunch of POPs in a specific region. So as you can see, these are all egress patterns. Actually, these are egress here. So you can see everybody's going to sleep in this region. It's going up, and then Cartographer starts load balancing these requests. So it's a very nice line there. And here's an example of this at a global level using all of our edge locations throughout the world. So you can see a lot of different egress patterns here, and as they go up, Cartographer is keeping them right where they need to be. So next I'll go through monitoring, but we don't have enough time. This is something in the longer version of this talk that I like to go into, but there's a lot of interesting ways to actually monitor this stuff, and A lot of ways to mitigate that so we don't have to be woken up at night. So I'd like to go through some of our open source components. ProxyGen, as I mentioned, is our L7 load balancer, and we've open sourced the ProxyGen parsing libraries for that. But ProxyGen can be, I think, easily replaced with Nginx or Hot Proxy or any other L7, TCP and SSL terminating application that you have. HHVM, Hip Hop Virtual Machine, runs all of our web stack. It's really nice, really fast. I believe Wikipedia just moved to it and had some really fantastic results. TinyDNS, our DNS resolver. IPVS, IP Virtual Server. We use ExaBGP to peer between our layer 4 load balancer and the routers. All of Facebook is basically glued together with Python, so I figured it deserved a mention here, and then as I'm also Zookeeper for our service discovery mechanisms. Photo credits, and here's a picture of the traffic team, and we thank you for listening. So, thanks.
Thanks, Patrick. That's fantastic. We've got time for some questions. Heads up.
Oh.
I should not be allowed to throw that thing.
Hey. I wanted to know, do you consider fragmentation inside the data center, or do you have a specific configuration of your Ethernet switches and routers inside the data center? Because you introduce IP over IP.
I'm sorry, can you say that one more time? My apologies.
Because of the introduction of IP over IP, you have a longer packet that can exceed the MTU.
Yes,
you have a specific MTU inside your data center?
Yeah, we do limit our MSS, so we do limit that down. We're not doing 1500. So, yeah.
Okay. I have another question. In the graph that you showed, the redirection from L7 load balancer to ECMP in another country, like with Germany and the other flag, the data crossing going from the L7 to ECMP, is it encapsulated within the IP over IP, or it's decapsulated?
No, so that's going over our backbone. We do MPLS, some other stuff there, but we're not doing any encapsulation at layer 3. Any label switching or anything's happening at a lower protocol.
Okay, thank you.
Cool. Any other questions?
So what are your major scaling pain points that you're hitting? Where are you running out of capacity?
Where are we running out of capacity, like from a physical perspective? Everywhere. It's really interesting because different regions have different requirements, I would say. Some regions do more video, which are less CPU intensive. Some regions do more photos, which is more CPU intensive. So I would say in general, from a infrastructure perspective, we always try to be limited by CPU. That's not always the case. I think it's easier to do in the data centers than the edge infrastructure. But in general, we try to do CPU, but it's not always the case.
Okay, right at the back.
So what do you guys do with people that use 8888 as the DNS provider?
Good question. So there's a lot of Googlers here, so correct me if I'm wrong. So one strategy that I believe Google DNS does, and again, correct me if I'm wrong, is when people use an open resolver like Google DNS, they will hit 8.8.8.8, and Google does something that's kind of nice for this, and they actually use an IP address that's in region. So they actually don't hit our DNS servers with 8.8.8.8. They actually use something that's local to the networks in that region. So that does help with that. The other way to do this, the better way to probably do this, is with client subnet. So client subnet is a way for a recursive DNS resolver to not give the IP address of the client, but they give the subnet of the client, and they pass that along to our DNS server. So that would be a better long-term way to do this. We don't do it today, but we're definitely looking into it, and we hope to do it in the very near future. That was a good question, though.
Okay, one more in the middle.
So assuming one of your data center dies, what do you do with traffic from the clients that have DNS record cached for that moment?
Good question. So we use a 1-minute TTL on DNS records. So hopefully, and since everybody in the world respects DNS TTLs, it's not a problem, right?
That's obvious.
So yeah, it's absolutely a problem. The problem isn't we don't give DNS records for our data centers. Everybody gets terminated TCP/NS and sell it to POPs, but it's still a problem. So there's a couple ways to kind of solve this. One is one thing I didn't mention. If I had more time, this talk was only focused on dynamic requests. So requests are going to hit a web server. But the other half of this is the CDN, so the static request for photos and videos. So we actually do a different load balancing. I'll try to give the TLDR. So the way it works is that map that's generated and thrown into our DNS server. We also have this map generated that's used by HHVM when it generates your newsfeed. So you're generating your newsfeed, and we already know all the images and videos that are going to be in there, right? So it actually queries the server, and we give you a DNS record, or we give you a host that's specific to a POP. So that allows us, if we do realize that the health is down for that POP, we can immediately turn it off. So we don't have to worry about DNS TTLs. We'll just immediately stop generating URLs in your newsfeed specifically to that POP. There's another strategy is with BGP, announcing them other places. We don't do that today, though. Yep.
Okay, Patrick, thank you.